Welcome to a lesson with Dr. Val. Let's take a look at a method called the least squares approximation, and we're going to look at it from a perspective of a left inverse. Okay, so suppose first of all, this is the setup for it at least, we're going to have an injective map, injective function. It's a linear transformation represented by a matrix A, meaning that its columns are going to be linearly independent, because when we find the Smith normal form, we're going to have kind of like an identity on the top and then zeros on the bottom. It's going to be longer that way, so that um, the the dimension of the range matches the dimension of the input here. Okay, so we have shown in a previous video that that means that this matrix right here has an inverse. All right, since it has an inverse, we can make this statement right here. And then we can rearrange it, regroup the multiplication in here like this to actually see that A itself has a left inverse. Okay. Now, not only does it have a left inverse, but this matrix that we just compute over here actually has a right inverse. So let's give these some names. So suppose that G is this part and F is this part as functions. Okay, so A represents a function, let F be that function, let G be this function right here. So between domain of F to codomain of F, we have F going here and G going back the other way. Now G itself going this way has a right inverse, it's F. G is surjective here, has a right inverse, and we get something very nice. G actually decomposes its domain, nice decomposition. And it decomposes by taking the image of F, and G is surjective, so it gets all of D. So we can just say F of D is it's going to be, it could be like a plane here, suppose, or it's a subspace of C, but I'm just going to represent it this way. So suppose it's some subspace here, and we also have, and then the kernel, it comes off of that. These are these decompose these right here decompose this codomain. Actually, they decompose it in a very nice way, is what we're going to see. We're actually going to see that they decompose it in an orthogonal way, which is kind of nice. Now, this K, what is it? It's actually the kernel of G itself. So the kernel of G, and then there F is the right inverse. So the image of the right inverse is this right here, and K, the kernel, is the kernel of function G. So G itself is decomposing the codomain. All right. So let's look at G for a minute, the way it's set up. This is an isomorphism. It has zero kernel. So the preimage of zero is only zero itself. This part right here, think about what it is. How do you matrix multiply by A transpose? We have rows. Those rows are the same as the columns of A. Columns of A represent the images of the standard basis vectors and the map A, which give you the range of A. So the range of A actually is like the span of the rows here of A transpose. So now when you matrix multiply, you're taking dot products of rows with columns. So we want all those dot products to be zero, which means all these guys, which represent the span of A, when you dot with them, you'll get something zero. So basically anything in the kernel, anything in the kernel of this part right here has to have all those dot products being zero, meaning that if you're in the kernel of AT, you're actually orthogonal to everything in the range of A, everything in the span of the rows, which is the same as the span of the columns of A. Now the range of A is just that here represented by this plane F of D, and K this kernel right here is going to be orthogonal to it. By that little description, the kernel is orthogonal to this because of the setup for how we actually wrote out our left inverse here, or our function g here, in this following way. So the kernel just comes from this part because this part happens to be an isomorphism. Okay, so we have a nice orthogonal decomposition of the codomain by G. We can see it right here. So we have any vector in the codomain, it can uniquely be written as a sum of vectors, one coming from the range f of d, and one coming from the kernel k of g. All right. So like this, r plus cursive k here, where r is, how do we compute it in the decomposition, what we saw in a prior video, where we looked at decompositions of this kind with a right inverse, is f of g of r. Okay, where in this case we're kind of swapped our g and f just because they represent different things. Here, f is actually the right inverse and g is the function. So, but it's the same idea. You run it's the same idea. You run g and then you go f to go back in the codomain. So b goes this way and then that way, and it's not an inverse on. Yeah, and it won't be an inverse over here on this side. I mean, it won't be an identity over here. So it'll change things up on this side. G is a left inverse to f, which means that you have the identity going on over here. So meaning if you first run f then g, you get the identity on this side, but not on this side. So things do change up over there. Okay, and you get this vector. This vector is the closest one that you can get to b that's in the plane here. The closest one. I'm saying plane, but I really mean just the subspace that's f of d. Okay, so the closest one. Why? Because this is orthogonal, right? That orthogonality gives you the closest one. Okay. So how can we use that? Let's use that in an example. For instance, what if we want to find the best fitting line to some points plotted in a plane? Well, we can take these points and put them into a form. Y is equal to mx plus b. We can input our x values and our y values, and we get a system of equations, right, with two unknowns. Take that system, think of it as a matrix equation like this, b and m. We don't know what b and m are right here. So where this b is a cursive b versus a print b, so we're differentiating between the two. And notice that we have, so 1 times b plus 0 times m represents right here equaling -1. So we can get these equations this way. This is an injective matrix right here. This is what we're trying to hit, and we're not going to quite hit it, because if we did, then all the points would match, and b would actually be in the plane that we're after. But we want to get the closest. We want to get the closest one that'll actually get us there. Okay, so this is the closest input value. Hopefully, we want to try to get the closest input value that'll get us, or the input value that'll get us closest to b here. Okay, so we go ahead and we do it, and the way we do it is we say this is the r value, that's the closest, and the input value that gets us the closest is g of b. Simply compute g of b, and that's going to be bm. So to compute g of b, we run through the process right here. A transpose A quantity, take an inverse. A transpose multiply it with negative this vector, this column vector right here, we end up getting this, which means that y equals negative a half minus 2/3 is the best fitting line. And in this picture right here, we can modify it slightly, okay, to get it looking where it should. So minus 2/3. And we have running through there, something like that, relatively, not exact, but we get the best fitting line. And we got it by using the that left inverse to A and just plugging in B. And we got the best fitting line. It's the line that most closely resembles those points right there. Thanks for watching.